So today I'm going to be talking to you about the slow neutron capture process in low and intermediate mass binary systems. So first things first, what is the slow neutron capture process? Or S process for short. The S process synthesizes elements heavier than iron through a series of neutron captures and beta decays in environments with relatively low neutron densities. The S process is very important as it allows low and intermediate mass stars to synthesize about half of the elements heavier than iron in our universe. I have here a snippet of what is known as the chart of nucleides. So the chart of nucleides shows all of the theorized isotopes and elements based on the neutron count on the x-axis and the proton count on the y-axis. The way the S process works is that we start with some nuclide. I have here strontium-87, and it captures a free neutron to strontium-88. And it captures another free neutron to strontium-89. However, strontium-89 is an unstable isotope, and before it can capture another neutron, it beta decays up to yttrium-89. And then we neutron capture, then decay, etc. So the key thing to note with the S process compared to the I and R processes is that the S process never ventures far from this pathway of stable isotopes known as the valley of stability. And the S process allows low and intermediate mass stars to synthesize elements as heavy as bismuth. However, there is a challenge here, and that is that we need a free source of neutrons because free neutrons are relatively unstable as they only have a lifetime of about 15 minutes. So how do we achieve this in low and intermediate mass stars? So the S process is active during the thermally pulsing phase of the asymptotic giant branch phase. I have here a HR diagram showing the evolutionary pathway for a 3 solar mass star, and the thermally pulsing phase occurs right at the end of the star's life before it ejects its envelope and transitions off into a remnant. However, anyone who has worked with thermally pulsing stars would know is that it's simply not that simple. Thermally pulsing stars are complex objects with varying regions of nucleosynthesis and stellar mixing, and they are characterized by what is known as the thermal pulse cycle, and this is driven by unstable shell helium burning. What I'm going to do here is I'm going to try and take you through step by step how a thermally pulsing star accommodates the S process. So the first step in our journey is actually going to be the third dredge up. So the third dredge up occurs when the hydrogen and helium burning shells temporarily extinguish, and the convective envelope penetrates deep into the stellar interior and will homogeneously mix all of the material above some convective boundary. The third dredge up is extremely important for low and intermediate mass stars, as it will transport the heavy elements synthesized within the center of the star up to the stellar surface. It is also important for the S process, because this convective boundary is not a hard boundary, and some of the protons actually manage to penetrate into the helium-rich intershell area. The exact mechanism upon which this occurs is not very well known, but these protons will fuse with some of the carbon, and they will form nitrogen-13. And what we are left with is an extremely thin layer. This drawing is not to scale, but we have an extremely thin layer where we have more carbon-13 than nitrogen-14. And this is known as the carbon-13 pocket. So the carbon-13 pocket sits right below the deepest extent of the third dredge up, and it remains there even after the star contracts and reignites the hydrogen burning shell during the interpulse. And during the interpulse phase, the conditions are just right for carbon-13 to fuse with the free alpha particles. And one of the products of this reaction are neutrons. So ladies and gentlemen, the carbon-13 pocket is the site of the S process. So just a quick recap before I continue. The slow neutron capture process allows low and intermediate mass stars to synthesize elements heavier than iron. And since neutrons only live for around 15 minutes, we need a local source. Low and intermediate mass stars create neutrons during the thermally pulsing phase through the formation of a carbon-13 pocket. Everyone following so far? Yay, got lots of nods, I'm happy. All right. However, my research, we focus on binary evolution. So what happens when we have a stellar companion? So stellar interaction may derail the stellar evolutions of the individual stars. So binary systems have this thing called the Roche lobe. But within the Roche lobe, the material remains gravitationally bound to the enclosed stars. However, should a star expand beyond the Roche lobe, mass begins to transfer from one star to the other, and this is known as Roche lobe overflow. So should the donating star have a radiative envelope like it does on the main sequence, it would likely encounter stable mass transfer. However, should the star have a deep convective envelope, like it does on the thermally pulsing phase, the radius of the star will fail to fall back within the Roche lobe, and as a result, the envelope of the donating star gets stripped off and is transferred relatively quickly over to the companion star, in what is known as runaway mass transfer. Now, you can imagine a thermally pulsing star may struggle to undergo any sort of stellar nucleosynthesis if it is missing its envelope. The companion star may also overflow its Roche lobe, and when we have two stars both overflowing their Roche lobes, we have what is known as a common envelope system, which may force our systems to merge. Observations show that around half of solar-like stars have a stellar companion, and this percentage increases with increasing mass. And a big part of my PhD is that we are investigating how binary evolution can impact a star's ability to synthesize and eject heavy elements. So what exactly do we do? So we use the binary population synthesis code, binary C, to simulate a grid of 640,000 binary systems at solar metallicity. And we do this for stars with a primary star mass of 0.8 to 8.5 solar masses. And from these models, we calculate the stellar yields. And the stellar yields are defined as the total mass of a specific nuclide that is ejected by the star over its lifetime. To describe a stellar population, we weigh the systems within our stellar grid based on the probability of that system forming. So what do we find? I have here a plot showing the barium that is ejected by a population of stars as a function of the initial primary or single star mass. Barium is an element that is synthesized through the S process. So at a glance, you may notice that there is a big region from the 5 to 8 solar mass range, but we are not seeing any barium production. And that is because that these stars are so massive that the temperatures at the bottom of the convective envelope actually become hot enough to sustain hydrogen burning. And this is known as hot bottom burning. And hot bottom burning blocks the formation of a carbon-13 pocket. We also don't see carbon-13 pockets in our low mass stars, simply because the third dredge up either just doesn't happen or it doesn't penetrate deep enough. The binary fraction here tells us the fraction of our population that is binary. So right now it is 0. So we are currently looking at the barium that is ejected by a population of only single stars. However, what will happen if we were to increase the binary fraction? So doing just that, looking back at this plot, so the solid colored region is the barium that's ejected by our population, including binaries. And for comparison with the red hashed area, we have our population of only single stars. And at a glance, we find that the inclusion of binaries results in 20% or a little over 20% less barium being produced compared to our population of only single stars. And this is mostly due to binary evolution, either truncating or completely preventing the formation of a thermally pulsing star. But we also find mergers can push stars up into this high mass region and turn on hot bottom burning and prevent carbon-13 pocket formation. However, overall, binary evolution will suppress the S process. But if we take a closer look, what does this look like? How does binary evolution change things on a system-by-system basis? Now, this plot here shows us the solar-scaled barium to iron abundance ratios that we calculate from the stellar yields of both of our binary and single star populations. And on the y-axis, we just have the frequency of these systems appearing within our populations. So if we look at our single star population, which is shown with the red hashed area, the maximum barium to iron abundance is about 1.6 dex. However, with binary evolution, we find that some of our systems are producing up to almost 2 dex, and this is mostly caused by mass accretion or a merger with an evolved star. So when this star gains mass, it enters the thermally pulsing phase, and it actually stays on the thermally pulsing phase for far longer than the star ever would while single, which means it experiences more thermal pulses and more opportunity to undergo the S process. However, these systems are relatively rare, as only 0.3% of our low and intermediate mass binary population has a barium to iron abundance ratio greater than 1.7. But the main key to take away here is that even though binary evolution on a scale of a stellar population will suppress the S process, there are some rare cases where the S process is actually enhanced. So just a quick summary for you all. The slow neutron capture process allows low and intermediate mass stars to synthesize elements as heavy as bismuth, and the S process is active during the thermally pulsing phase via the formation of a carbon-13 pocket. when we have a population that is 70% binaries, this population produces a little over 20% less barium compared to our population of only single stars. But we find that binary evolution can lead to some systems being enhanced. For those of you who are more interested in the details, we have a paper that's currently under prep, so keep an eye out for that one. Anyway, thank you all for sticking around till the end of the day. If you are interested in some of the other work I've done, I do have a website where you can find papers, posters, things like that I've done. Anyway, that's it from me. I'm happy to take any questions.
Thank you very much. Any questions? Very interesting talk. So in this zone in which you have this carbon-13, it's continually making neutrons, and as they decay, it makes new ones, so that then you can use the slow process to synthesize the helium.
To my understanding, that's what happens. Yeah.
Okay. Any other questions?
A question on the metallicity dependence of the S process. So during the population synthesis of the S process yields with single and binary stars. So I guess that to get the heavy elements, you need them to be contained in star originally, right?
Yes, so you do need some like seed nuclei for the neutrons to begin.
Right. So what is actually the sort of the lowest metallicity that you need to have for stars in order for the S process to work?
I don't actually know that exact number. I know the S process is actually more efficient at lower metallicities, but I don't know the lowest boundary for the S process to begin. I